The last video showed that our atmospheric circulation is split into 3 cells in each hemisphere: the Hadley cell, Ferrel cell, and polar cell. In this third video in the Global Circulation series, we will look at the winds within these cells and how the rotation of the Earth influences these winds to give us jet streams and prevailing wind patterns. As well as being split into 3 cells, the global circulation pattern is at an angle due to the Earth's rotation. The spin of the Earth induces an apparent motion to the right in the northern hemisphere and to the left in the southern hemisphere. This is the Coriolis effect. The key to the Coriolis effect lies in the fact that the Earth's surface rotates faster at the equator than at the poles. This is because the Earth is wider at the equator, so has further to travel in one day. The result of this means that as air moves away from the equator, it doesn't move in a straight line relative to the Earth's surface. Instead, it appears to an observer on the ground to move in a slightly curved direction. But there is no physical force causing this deflection. As the atmosphere rotates with the Earth, it is just due to the air flowing from a region that is moving faster to a region that is moving more slowly. To explain this further, imagine an air parcel as a ball. The ball is thrown from the equator towards a point near the North Pole. Even though it moves in a straight line, the ball will appear to an observer on the ground to curve away and land to the right of its target, as the point near the North Pole is moving more slowly and is not caught up. If the ball is now thrown from the North Pole towards a point near the equator, it will again appear to a surface observer to land to the right of its target. But this time it's because the Earth's surface at the equator is moving faster and is moved ahead of the ball. This effect only happens on objects that are in motion. This deflection is a major factor in explaining why winds blow anti-clockwise around low pressure and clockwise around high pressure in the northern hemisphere and vice versa in the southern hemisphere. So when flowing towards the North Pole, air is deflected towards the east, and when travelling southwards back towards the equator, it is deflected westwards. The same overall result occurs in the southern hemisphere. How does this lead to eastwards flowing jet streams and prevailing winds? As air moves away from the equator at the top of the Hadley cells towards higher latitudes, it starts to be deflected by the Coriolis force. Just as a skater spins faster by bringing their arms and legs closer to their bodies, air moving away from the equator speeds up as it gets closer to the Earth's spin axis. This process is known as the conservation of angular momentum. The magnitude of the Coriolis force increases towards the poles, so by the time the air reaches 30 to 40 degrees north or south, it is moving in an eastward direction. This subtropical jet stream occurs high in the atmosphere between 12 to 15 kilometres. It is associated with some of the strongest winds on Earth, reaching over 280 miles per hour at times. As this jet sits between the descending branches of the Hadley and Ferrel cells, there is little associated weather. The polar front jet forms in a different way. This jet sits between the rising branches of the polar and Ferrel cells. It marks the boundary between cold polar air and warm tropical air, known as the polar front. The polar front jet occurs at a height of 11 to 13 kilometres and is primarily the result of the temperature contrast across the polar front. The stronger the temperature contrast across the front, the stronger the jet. So it follows that the polar front jet is stronger in the winter than the summer. Waves or ripples along the jet stream can cause Atlantic depressions to deepen explosively as they are steered towards the UK. Winds at the surface are also subject to deflection from the Coriolis force. The surface flow of the Hadley cells form the persistent trade winds. As air flows towards the equator, it is deflected towards the west in both hemispheres. forming the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. The persistence of these winds allowed sailing ships to cross the Atlantic and opened up trade routes between Europe and America, giving them their name. The surface wind in the Ferrel cells would flow from a southerly direction in the northern hemisphere, but the Coriolis effect causes this wind to be deflected to the right, leading to the prevailing westerly and southwesterly winds often experienced over the UK. This setup is not unique to our planet. Jupiter also has circulation cells similar to those on Earth. A day on Jupiter lasts for about 9.5 hours, so it is rotating much more quickly than the Earth. The great size and fast rotation of this planet makes the Coriolis effect very strong. This splits the Jovian atmosphere into many circulation cells in each hemisphere, producing numerous alternating bands of rising and falling air and giving Jupiter a distinctly striped appearance.